then we can directly move to.
Yeah, you
so
go.
Noel, I'll start if you want to start recording. So today we have the great pleasure of me introducing Professor Ghassan Chehab as today's Kent seminar speaker. Professor Chehab is an associate professor in the Department of Civil and Environmental Engineering at AUB, the American University of Beirut in Lebanon. He received both his bachelor and master's degree from AUB, and he earned his PhD in 2002 from North Carolina State University. After finishing his PhD, he did a postdoc at NC State. Then it was followed by being a pavement structural engineer at Indiana DOT, the Division of Research. Then after finishing that, he was an associate assistant professor at Penn State University. Then from there, he went back to Lebanon, and where he's now an assistant professor at the UB. His area of research and teaching include advanced characterization of asphalt binder and asphalt mixture, pavement design and management, and sustainable construction materials. He serves on multiple, as an editorial, on the editorial board of multiple journals, and also he is a very active member in many professional society in the pavement community, such as APSI. Today he will be giving us a presentation about rutting in airfields. And as usual, no questions will be allowed during the presentation. The presentation will be 40 minutes followed by 20 minutes questions and answers. If you want to ask your question yourself, you can raise your hand by the end of the presentation by going to the participant tab and then click on raise your hand. So I'll give you the option of doing that. And the other option is you can write your question even throughout the presentation. You can write it in the chat and I'll ask it on your behalf at the end of the lecture. Without any further dues, please join me in welcoming Professor Ghassan Chehab.
Thank you, Isaac, for this very nice introduction. It's an honor for me to have been asked to come and offer some of my knowledge in the area of asphalt pavements related to airfields. I thank Dr. Al-Qadi and all his staff and students for making this happen. I'm gonna share my screen now. Okay, can you see the screen?
Not yet.
Not yet, okay.
Now we can see your screen. We cannot see the presentation. Yeah, we can see it now, Professor.
Okay. So today I'm going to be telling kind of a story, actually, of an endeavor that we went through, myself and some of my students and colleagues, in investigating certain asphalt rutting failures that took place in a couple of different airports in hot climates. So I just wanted to share with you these findings and these some interesting facts that we came across that I think are important for you guys to have in mind whenever you're dealing with asphalt airfield pavements. Life is full of successes, okay? You know, we can build so much successful projects with good design, good material selection, good construction, good quality control, good maintenance, you know, all these technologies out there. But you know what? We often have failures. And unfortunately, some failures, you know, are expensive not only monetarily, you know, but expensive because of the inability to fix quickly, particularly when you are talking about airport runways that literally cannot stop, cannot shut down. So unexpected premature failure would probably cause chaos. So while we can seal a crack quickly on the road or fix a pothole on the road in a runway, it's a much more complicated and much more costly to have a mistake done. But these failures happen, and what you're seeing here in the screen now are, you're seeing 3 different pictures showing rotting in the asphalt layer. And if you take a core in all of these 3, the rotting is not in the subgrade or in the unbound layers. So the pavement design is good structure-wise, but something's wrong in the material of the asphalt layers, because the asphalt layers are what really rotted. And again, more failures. And we see it in so many different places, particularly, again, in hot countries. So failure, according to Forbes, failure is success if we learn from it. So if we know exactly what's going on, then bingo, the next time we build it, we're going to do it right. So the question becomes now, why are some airfields with proper binder grade selection and a good mix design, sometimes SMA, when you select the proper binder grade, good mix design for the asphalt surface layers, why do you have asphalt rotting? I mean, isn't it a straightforward thing? You select the proper PG grade, a good interlock skeleton in the aggregate, then you shouldn't have asphalt rotting, but it happens. Well, let's concentrate on those failures. Let's see why these asphalt ruts are happening and investigate them with a bit of rigor and comprehensively, looking at all angles, everything together to understand, what I call the 4 W's, or what went wrong and where. First thing, the first problem that happens is that we guys are teaching and we're doing research online from home. So we may have to leave our offices a bit, leave our homes, and go to the field, go to these pavements while they're being built, feel the heat, get some hands-on experience, and learn the small tricks of the trade. So that's a kind of joke set aside, but it's just true. We do need more hands-on experience. I have this quotation. I found this quotation, and it made me a bit surprised. It said, "Asphalt rotting is an insignificant distress mode in airports." I'm not going to say it's fake news, but let me just say it's false news, okay? Throughout the decade, in the last decade, there have been multiple failures documented in various airports. Some of them high-level failures, such as one in San Francisco, in Dubai, Doha, Kuala Lumpur, a couple in Australia. I've seen ruts that are as deep as 7 centimeters, up to 3 inches. And I've seen pictures of ruts that are as thick as 15 centimeters. Okay, so we're talking about 6 inches. The whole asphalt layer is rotted. So there are problems. And when we're talking about airports, first thing that comes to mind, high tire pressure, very heavy aircraft. The traffic might be slow during taxiing or waiting for the plane to take off. Is the binder too soft? Was the climate exceptionally hot? These things that come to mind whenever you get these rotting failures. Now, for highway applications, really, SuperPave was clear in what to do with respect to high temperature binder grade. After you select your binder grade based on the climate conditions, then they tell you they recommend to bump up the grade by one high temperature binder grade if you have slow traffic. And if you have stopping traffic, bump the binder grade by 2 grades or 12 degrees C. So it's straightforward based on research. And later on that was modified a little bit in SuperPave Plus. But again, there were recommendations made regarding how to solve the issue of speed by bumping. Now, when we bump, really, by default, we take it that we're going to bump the surface layer, the PG grade of the surface layer, especially if the surface layer itself is thick and is made of 2 lifts. Directly, your mind goes to bumping the PG grade of the surface layer because that's where the high stresses are. That's where the high temperature is, basically. So deeper asphalt layers, they experience lower temperature, so it might be okay not to bump. And going very high in your binder grade requires you to put some polymer, fibers, modify the asphalt, which basically bumps up the price a lot. So you want to save at the end of the day as much as possible, of course, when you go to the bottom layers. And so it is common practice to apply grade bumping just to the surface layers. A lot of DOTs, a lot of highway agencies actually stipulate that. That's only the surface layers that are subjected to grade bumping. Now, we come to the binder specs for airfield pavements. So in the specs of civilian airfields, you go to FAA's advisories, you go to the military airfield guides. As you can see that quote at the bottom of your screen. So in AC 150 edition G, it reads, typically, rutting is not a problem for airports. Grade bumping should be applied for the top 125 millimeters of paving at locations where stacking is expected at ends of runways and taxiways. So 125 millimeter, we could still be in the surface layer. You might be hitting the start of the binder layer or the base layer, but typically 125 millimeter in an airport, you're pretty much talking about the surface layer. And again, they say rutting is not a problem for airports. And this is quite, to me, it's quite confusing. Why is it not a problem? Now, and later on in the H edition, they kind of rectified a little bit the recommendation, and they said, hey, if the gross weight of the airplane is between 12.5 kips and 100 kips, bump by 1 grade. If the airplane is going to be, if your design aircraft is going to be more than 100 kip, bump your binder grade by 2 grades. And now, if you have slow or stationary areas where there's slow or stationary aircraft, such as the end of taxiways, beginning of the runways, then even if you have less than 12.5 kips, bump 1 grade, and then 2 grades, and then 3 grades as the load of the aircraft go higher. But there is no mention anywhere of the depth to which the PG grade bumping is recommended. Asphalt pavements, sometimes the thickness goes to 50 centimeters. I mean, you could have very thick asphalt pavements. So what do I bump? Till where? Till where? You might have 5, 6 lifts. Okay, 2 lifts for surface, 2 lifts for intermediate, 2 lifts for binder layer. So which ones do I bump? Which ones do I not? So there wasn't really a clear guidance on that. But again, by default, one takes it that let me bump the surface layer since it's feeling the maximum stress and the highest temperatures. Again, some of the cores now that we went and took for those rutted asphalt airfield pavements really showed us that there is need to investigate asphalt rutting failures that are not caused by inadequate asphalt mixture properties in the surface layer. So surface layers are fine. In a lot of rutted runways and taxiways, surface layers are intact. So we need to consider the reasons behind why the asphalt intermediate layers and the asphalt base layers at times themselves contributed to the majority of the rutting. So there is now a problem. It has been confirmed that intermediate layers and base layers of flexible asphalt airfield pavements can rut and do rut. So we need to do something about it. What? Well, let's see. Do we need to bump up the grade, change the mix design? What should we do? That's the objective of the story I'm telling you now. Just to go and explore and see what is that asphalt in the intermediate layer or base layer. What is it feeling? What load is it feeling? How long is it feeling that load for? What's the temperature of that intermediate layer? Are these all conditions, do they really necessitate grade bumping or not? So that's that's the motivation behind this work. Now, the common approach of designing the pavements is, okay, you put your best material, the highest quality material at the surface, because that's where the highest stresses are. And as you go down, you tend to loosen a little bit the material quality with depth. You put cheaper material as you go down. So you end up with a very stiff, well-performing mix at the top, polymer modified and an SMA and what have you, but it's not, the quality doesn't match that when we're talking about intermediate layer and base layers. Now, the French have a different approach. They do tell you that, you know what, I do want a stiff base layer in the pavement. I want a stiff intermediate layer. The surface layer can be a bit softer because it is going to age, short-term and long-term age, and it's going to be subject to densification in the first year or two. So don't worry about it. Surface layer is going to become stiffer. Just make sure that the base layer is stiff. So that's the other approach. Now, what are the challenges? There is complex loading mechanisms in airfields. Large gross weights, we're talking very large gross weights, and the tire pressures are much higher than what we experience in highways. You have wide range of traffic speeds. You know, the plane lands at 300, 400 kilometers per hour, all the way to stopping. So you have taxiing. Airplane can taxi at 5 meters per second, all the way up to 30 meters per second. So there's variation of speeds for the given location. And then you have to channelize trafficking. I mean, with the ILS now, with instrumented landing systems, pretty much all airplanes are landing at the same spot. If they have the same gear configuration and distance between the gears, they're repetitively landing on the same spot. So you have much more channelized traffic than you have in the case of highway. Less wandering, which contributes to rutting and something that needs to be dealt with. Now, there has been some programs like the Airfield Asphalt Pavement Technology Program, AAPTP, that dedicated mostly one full research project to address binder selection and part of another research project to address binder selection. But really, they looked at the importance of incorporating aircraft tire pressure as a factor, but there was an avoidance of stating upfront that high temperature PG grade for deep layers needs to be touched. That wasn't touched upon at all. So that was still a gap that needs to be filled. Now, we want to analyze our pavements. We want to see what's going on. Then we need to do it right. We want to do it rigorously, I said. We want to do it comprehensively. Accurate performance prediction means step one, you need accurate material characterization models that you need to incorporate in your analysis and in your design. So for analyzing the pavement structures for these airfields, we chose to use Flexpay that does mechanistic analysis, and that was developed at North Carolina State University by Dr. Richard Kim, who also helped in some of the some of the material that I'm presenting today. Flexpay is a 3D finite element program. It incorporates viscoelastic, linear viscoelastic, and viscoelastic continuum damage models, and it incorporates viscoplastic models, the shift model, to characterize the accurate behavior of asphalt concrete in its linear range and in non-linear range, both low temperatures where you might have cracking and high temperature where you may have rutting. It is capable of analyzing moving loads, and as far as rutting is concerned, it's purely mechanistic performance prediction. You don't have to worry too much about using empirical performance prediction models that have been calibrated based on truck traffic, and suddenly you want to adapt it to truck traffic. I mean, you don't have all these tricks that empirical prediction models play. So just to go quickly, if you want to do this correctly, we need to analyze three factors, or look at three factors. What are the compressive stresses that are being subjected on the pavement? What is the loading time? How much time are these loads staying? That's very important. Another important factor is, what is the pavement temperature when these loads are being applied? Now, we have to deal with the various configurations of that the different airplanes have, because those do affect the compressive stresses and the loading time. So a 777 will have three tridem axle, dual tires. A320 or Boeing 737, in the majority of the airplanes, have a single axle. Again, and if you want, you can compare it to a 80 kilonewton easel and see how the loading changes. Also, what changes are the speeds. So you could be taxiing slowly on a taxiway at 5 meters per second. You could be taxiing pretty fast along the taxiway, up to 10 meters per second or 20 knots. And then at the runway, the minimum taxiing speed is 30 meters per second. So you have a variety of traffic speeds that can happen. And all these different traffic speeds do affect the compressive stresses being felt and the loading time. So the traffic speeds need to be looked at when we analyze our pavement, and the loading configuration needs to be looked at. When we're looking at the first step in material characterization, we say, let's just measure the linear viscoelastic unit response functions. Let's easily do the simple performance test or the dynamic modulus. So here in front of you, we have three mixes, A, B, C. Mix A, polymer modified mix for the surface layer. And the mix B and mix C were mixes that were used for intermediate layers in pavements in runway pavements in hot areas. So those are actual mixes. Those are the actual dynamic modulus master curves. To be able to ease the modeling and to input the material characterization in Flexpay, you had to convert it to relaxation modulus, E of T, and represent it in its Prony series format and input it to take care of linear viscoelasticity. Then that takes care of linear viscoelasticity. So we're suffering from rutting. When we have rutting, we have permanent deformation, we have plastic flow and shear flow. So the viscoplastic model now needs to kick in if you want to analyze what's going to happen in the pavement beyond the linear range. Again, Dr. Kim recently developed the viscoplastic shift model. And the viscoplastic shift model is based on what is referred to as the stress sweep rut test, the SSR test. That also can be done on the AMPT. It's a pretty simple test. But this test allows you to collect several viscoelastic strain data. And that data includes various deviatoric stresses that you're going to be applying. You're going to be applying various loading times, and you're going to be testing at different temperatures. With these differing, you will be using the time temperature superposition principle, which is valid with growing damage, and the time stress superposition as well, okay? With those two, so you have two shift factors, one for stress and one for temperature. Then you create, similar to a dynamic modulus master curve, you can create a viscoplastic strain master curve at reference conditions. So never mind what your temperature is, never mind what your loading time is, never mind what the stress is. If you have the viscoplastic model, you can use the shift factors to predict the viscoplastic strains using the master curve that you have by shifting the loading conditions to the reference conditions. And the model represents or can take care of the primary and secondary regions of the rutting evolution curve. And again, it can account for the various combinations of loading conditions. And the SSR test is simple, it's short, and it can be done in one day. Now, I don't want to go too much into the viscoelastic shift model here. All what I'm showing you here is that we figure out what needs to be figured out are what is the time temperature shift factor. And you can do that by testing the asphalt at various temperatures. What is the vertical stress shift factor? And you can do that by testing at different deviatoric stress levels. And once you have these shift factors, you can combine them together to form one universal shift factor. That's why the model is called the shift model. And then once you have that shift, the overall shift factor, then for any stress at any temperature, you can convert it to a reference stress at a reference temperature and predict the response for your input. In red here is the viscoplastic strain formulation. So it is basically a function of N reduced here. N reduced is number of cycles, number of loading cycles. And it's reduced because these cycles could be due to various loads at various temperatures. You have to convert them to reference conditions, and then those cycles will become reduced cycles. So N reduced is basically the number of cycles at your reference conditions, epsilon 0 and I and beta now are the fitting parameters. So each mix has one set of fitting parameters. Once you find these fitting parameters, now you can predict the viscoplastic strain for the material for any loading condition you have. So we need to find these three by doing the SSR tests and measuring the viscoplastic strain and fitting these parameters. This is how it looks like. You're going to be doing the SSR test at 2 temperatures, a high temperature, which is a function of the climate, and you will be doing a series of sinusoidal cyclic waveforms at different stress levels, the Vitoric stresses, for a given loading time and a given rest period. You're going to repeat doing loading blocks at another temperature called the low temperature, T low, which is a function of the PG grade of your mix, and you're going to do the Vitoric stresses at the same levels. Now, the determination of the test temperatures is dependent on the climatic zone, because we're looking at degree days at T high. PG grade of the binder is also important to determine these testing temperatures. So we're going to confine the specimen with 10 psi, and we're going to be applying sinusoidal cyclic waves in different blocks and measuring the viscoplastic strain that accumulates as we test all 600 cycles at 2 temperatures. Now, I was discussing with Dr. Richard Kim about these values, and Dr. Kim said, you know what, let's bring the loading regime that we apply in the SSR test, let's bring the stresses a bit higher, because the stresses that are passed down to the pavement by the gears of the airplane are higher than the stresses we are testing the mix at to develop the model. So, optimally, you would like to test the mixture and develop the model using stresses that are close to those in reality that are going to be applied. So what we did is we increased the Vitoric stresses by 100 psi, and the confining pressure we added 20 psi. So now we have higher stress conditions, and so this is kind of a modified testing protocol to develop the material model and predict its performance under heavy loads in the airfield setting. So what we did is, we had mixes from these airports that we were able to mix, and they're from different parts of the airport, from different elements. So we brought these mixes and we came up with their dynamic modulus, and then we applied the SSR tests to them, to the surface mixes, to the binder mixes. We had various replicates. As you see in the surface mix, for example, the surface mix was good, it was stiff, and it just, the rutting was just like 1 millimeter, which is after 600 cycles, which is low. And, there is some consistency. The 6 or 7 specimens tested really yielded the results that were very close to each other. When we tested the binder mix, or the mix of the binder layer, first we saw high permanent deformation, up to 4 millimeters. So the binder layer did deform much more than the surface layer, and there was so much discrepancy, or there was a high variability between the specimens that we tested. So this was the first clue that, hey, what's happening with the binder mix and the binder layer of that pavement, of the runway? Was quality control bad? The mix design bad? What's going on? So that was the first clue. This test were done at T low, which happened to be 38 degrees Celsius in this case. At T high, which is 60 degrees Celsius, we also brought specimens and we tested them using through the SSR. For the surface mix, again, we got consistent viscoplastic strains up to 4 or 5 millimeter. But the binder, again, binder mix at 60 degrees C gave us a lot of deformation, up to 12 millimeter rutting, which is very high. And again, there was a big discrepancy and variability between different specimens. Again, each specimen came from a mix from a different locations. These mixes we're testing are from the same airport, but some are from taxiway C, some are from runway W, in the west runway. So they're from different places, but the same mix design though. Okay. So maybe there was a problem in mix fabrication or in mix laydown and compaction. Now, so what we did is we averaged these curves, the viscoplastic strains of the various replicates at T high and at T low, and we fit the viscoplastic model, the shift model. Remember, there are 3 coefficients that we need to determine to model a certain mix using the shift model. So we fit the viscoplastic shift model to the data we had, and you can see that the shift model was able to capture the behavior, the response, the viscoplastic response of the surface mix and the binder mix under the loads of the SSR test. So the model works. The model can predict the behavior of asphalt at high conditions with high viscoplastic strains being accrued. You can see here, this is the binder mix, again, which is basically, if you look at the bottom screen, the strains being predicted are high. And you can see that at T low and at T high compared to those at the surface mix. So we found, we tested the mixes in dynamic modulus, converted them to relaxation modulus, got the Prony series for both the wearing course and the binder course, or the mix of the wearing course and the mix of the binder course. And for the SSR model, the shift model, we got the coefficients for the wearing course and the binder course. So now we have complete material models for the mix in the surface layer and the mix in the binder layer. We move on now. Before we run the analysis and see what are the responses of the pavement structure now to a moving load, we wanna investigate several factors. We're gonna run a control scenario first, where we say that I am gonna run a Boeing 777. That's my control case, my reference scenario, on one layer, 40 centimeter thick, and I will use mix A for it, and I'm gonna do it at 10 meters per second. But then I wanna know what is the effect of the gear type on the performance and behavior of the pavement. So I will try to change the gears and apply the gears of an A320, and I will try to run an easel, specify an easel, and look at the viscoplastic strains, how are they gonna change, keeping everything else constant. And then I wanted to study how does speed affect the viscoplastic response. So for the same airplane, I will run it at 2 different speeds, at 5 meters per second and at 30 meters per second, and compare it to the control case where it's 10 meters per second. So now I have the same airplane moving at different taxiing speeds, and I can see how the viscoplastic strain is changing with that speed. And then I'm gonna look at the mixes themselves, the layers themselves. So I will try having one mix using one layer with mix B, then 2 layers, surface layer and binder layer with mixes A and B and mixes A and C. Everything else is fixed, the speed, the gear type. All I wanna do is to see how do softer layers behave, how do stiff layers behave in the context of viscoplastic strain under gear loads. What the results told us are the following 3 things that I would like you to take away from this presentation. 1, deeper layers are subjected to high compressive stresses. When you go deep, compressive stresses in airfield pavements are still very high. 2, compressive stresses in the deeper layers are applied for considerably longer loading times compared with surface. So this intermediate layer and base layer is feeling high stresses. But not only that, these stresses are lasting for a long, long time. And that's damaging, because we know the longer the loading time, the creep effect, you will have much more creep strain and you might get damage. The third thing is temperatures now of deeper layers are high for extended durations compared to the surface. So I have also temperature to worry about. Deeper layers have high temperatures and they last for a long time, as you will see. So here, what you see in this graph is basically, I'm comparing the stress profile along the depth of an easel, 80 kilonewton easel or axle of a standard truck. I have the gear of an A320 and a gear of a 777, Boeing 777. First of all, you can see that The stresses on the contact area on the surface are approximately twice as high as that of a truck, of an easel. So you're talking about double the applied stress at the surface on top. Second, which is very important, if you look at an easel, the stress keeps going down and it decreases up until it's at 15 centimeter. Then there's an inflection point. And then the stress reaches a low point, and then it starts to taper down and become small and constant, reaching an asymptote. Well, if you look at the A320 and the Boeing, the stresses remain still high. They are decreasing, but they're still high in magnitude. It's only until 30 centimeters deep that they reach low values of stress that then taper down and form an asymptote vertically. So what's the take from this? Well, stresses are very high in airfield pavements when in the deep layers, unlike highways where you have trucks on them. The stress that a truck imparts, that an axle imparts on a pavement is 800 kPa. That stress is much higher for airplanes. Actually, that 800 kPa is only felt after you go down to 18 centimeters or 21 centimeters deep in the pavement. That's when you see the 800 kPa. Everything above it is much higher. So whatever I'm doing for a highway pavement in SuperPave for grade bumping, I'm worried about 800 kPa, so I'm bumping up the grade. Well, that 800 kPa is still there in the airfield pavement, but it's not at the top. It's even much deep. So so the deeper layers something needs to be done for the deeper layers. Can they take that high stress? I typically don't optimize my binder layer to be top notch, but yet I'm seeing stresses are still high. And then I come to the extended loading time. We have an 18 kilonewton easel. It's traveling at 10 meters per second, which is like a taxiing speed. If you see here in the first, at 0 centimeters at the surface, load is felt for 0.02 seconds. At 30 centimeters deep, the load is felt for 0.2 seconds. Go to the extreme, Boeing 777. You have tridem axles, and look at the figure. At 0, at the surface, the load is felt for 0.07 seconds, a longer time. The stress is much higher, 1520 kPa. But at 30 centimeters in deep, 30 centimeters, you're not in the surface layer. You're in the intermediate layer. The load is felt for 0.6 seconds now, compared to 0.2 for an easel. And the stress is 400 kPa compared to 60 kPa in an easel. All of that is because when you have that tridem axle passing, the load is felt for a much longer time than when a single axle of an A320 passes or when an 80 kilonewton easel passes. So loading time is applied for a long, long time. And that's going to hurt us and cause a lot of viscoelastic strain. So we need to keep that thing in our minds. Look at speed. So again, the slower you are, the faster you are, the lesser the loading time and the lesser the stress. So slower traffic, 5 meters per second, is going to give you higher stresses for longer times, 0.8 seconds at 750 kPa, compared to 30 meters per second, which is going to give you only 0.15 seconds and just 400 kPa. So slow loads can still affect you deep down in the layer, 30 centimeters down. The speed effect is still there. Let's look at temperatures. So I took the temperature of Dallas, Texas. It's similar to the temperature of where the airports are. At the surface, temperature goes from a low at 3 a.m. of like 22 all the way at 3 p.m. to like 65 degrees Celsius. So you have 42 degrees Celsius difference at the surface. So the hot temperature, it's reaching 65 C, yeah, but you know what? Not all the time, because it's going to go 42 degrees, it's going to cool down by 42 degrees Celsius, okay, by the time it goes from 3 p.m. to 3 a.m. So the high temperature is felt for only a specific window of time. If you go a bit down, deeper, the average temperature is a bit less. It's not like 40, it might be like 38 C. But you know what? its range is smaller. It's only gonna change from 28C to 48C, 10 degrees C the difference. So temperature is, yeah, the average is high, 38, but it's gonna be, its range is also high. If you go even deeper now, so you go to like 35 centimeter where the binder layer is, the average temperature is like 35 degrees C, but guess what? It's gonna last 24 hours at 35 plus or minus 1.5 degrees Celsius, meaning high temperature is gonna stay there the whole day and the day after that. So you have a high temperature, even if the load is smaller, but the high temperature is always there. And that's gonna soften the mix. And this is a game changer. The fact that temperature is very high at the bottom for a long time is gonna kill you because of that extended time with high temperature. Now let's look at so we looked at the stresses. Let's look at the strains for a 777 and 320 for airplane gears. The maximum strain is being felt at 15 centimeters deep, guys. So it's at 15 centimeters below the surface where the maximum strain is measured. If I look at the ESO, it's at 5 centimeters. And we always say the top 5 centimeters are the most critical for rotting in pavements, and we measure the temperature at 20 millimeter or 25 millimeter from the surface because that's where rotting occurs. Well, you know what? Strain for in airfield pavements under airplane gears, these strains are not, the highest strains are not at the top. They are deeper. They're like 15 centimeters deep. They're higher than on the surface. So I don't want to fix the surface and make it top notch and neglect the lower layers. Look what the maximum strain is happening. And you know what? The 777 strain is basically 2 times the strain of an A320. It's about 6 times the strain of an ESO. And it's slower. So not only is it lower, it's also very high. Let's look at the effect of loading time. At 5 meters per second, for a 777 now, at 5 meters per second, very slow, I'm gonna get a strain that's maximum at 25 centimeters deep. That's where the strain value is maximum, at 25 centimeters deep, guys. So I need to take care of my binder layer. That's where the maximum strain is happening for very low speed aircraft. It's like a 777. Looking at different mixes, soft binders versus soft binder layers versus stiff ones, while the softer are giving me much higher strains. Okay, so soft binder courses will be problematic. Look at this difference. They will deform twice as much as the stiff binder course. Let's apply this to a case study. We have 2 airports, similar climates, similar aircraft fleets. One airport did tremendously well, one airport did not. And I plotted here the dynamic modulus of the base layer and surface layer for 2 airports. We have a problem with the master curve or the stiffness of the soft layer, the base layer of airport A. So airport A, the base layer, asphalt layer, was too soft compared to the base layer of airport B or the surface layers. So that is a problem, soft base in airport A. And let's see what it's gonna do compared to the other airports. So airport A suffered from severe asphalt rotting a few weeks after opening for traffic, whereas airport B has performed adequately with no rotting over several years. Huge difference. If I look at the viscoplastic strains produced, just look at this. Look at airport B, the base mix, the base layer. It rotted at 60 degrees C by the problematic was the base, the airport A is the base mix is the problematic. So it rotted at 60 C by 0.06 strain. 0.06 strain resulted after 600 cycles at 60 C. For airport B's mix, base mix, it only rotted 0.004. Here it is 0.06. So more than 10 times more strain in the base layer of airport A. That's how much that's in viscoplastic strain. That makes, because it was soft, that's what it's giving me in viscoplastic strain. And you know what? When I predicted all the rotting, the blue the blue line is the rutting predicted to happen in airport A in the surface layer. And the error bars here is the variability. So the maximum rut is at the top, the error bar, and the minimum rutting is that straight line. So all in all, the maximum rut due to the surface is about 1 millimeter. If you look at the top, that's the rutting occurring in the base layer, in the binder layer. So you have like 4 to 5 times more rutting happening in the base layer below, more than the surface layer at the top. So I want to say one thing. Properties of deep asphalt layers, intermediate or base layers, are critical for asphalt rutting in airfields. This results warrant revisiting the PG grade bumping recommendations for airfields to deep asphalt layers. We're going to take 2 minutes. I know I'm right on time. Just to show you, we compared our predictions to the actual measurement of the rut in these airports. We had all the fleet information. We plotted the deformations due to the different airplanes, 777, 320, 330, 350, 787. We converted them all to equivalent gear factors, meaning the equivalent to a B777. So the B777 is our reference plane now. It's like an ESO, but now I'm going to call it an EGF, equivalent gear factor. And I transformed the damage done by the other. I calculated the damage due by other planes and divided it by the damage of a 777 and came up with EGF. And then this is a snapshot from the Flexpay. You could look at the left gears, the right gear, and under 2 of the tires, what the displacement is looking like. And what we predicted is the following. So we had good mixes collected at the runway, and we had bad mixes collected. First of all, the good mix, which is in green, at 100 meter and blue, 100 meter per second, didn't give lots of rutting in our prediction. The green, which is 30 meter per second, but it's a good mix, not 100 meter per second, rutted a bit more. And the fair mix at 30 meter per second rutted higher. Well, when we went to that runway, the minimum rut measured was this green. The maximum rut measured was 1 centimeter. So our predictions are perfect. I mean, within 1 centimeter, we're talking about. And the ranking of these mixes is very good. For the taxiway one, again, we had a fair mix, which is the orange one, and a poor mix, which is the brown. So this is where our predicted from the model. When we went and measured, we found out that along that taxiway, minimum rut was 0.5 centimeter, maximum rut was 2 centimeters. And after 4 years, again, we had minimum rut and maximum rut along measure, and our predictions fall just very nicely in between those. My last slide, another taxiway. These were the measured rutting at year 1 and year 4. The green is the minimum rut along the taxiway. Red is the maximum rut. Our prediction to 20 years using the viscoelastic model, using the shift model, using Flexpay, was in between the minimum and the maximum measured on the runway. That's excellent. And I'd like to acknowledge, I know I ran a little bit beyond my time. I'd like to acknowledge Dr. Richard Kim at NCSU. He is my advisor. He will always be my advisor. His work on Flexpay, his work on the shift model were instrumental in making this work happen. I'd like to thank Dr. Hussein Asim, he's my ex-PhD student. Now he's a professor at Beirut Arab University. Ms. Yara Hamdar, who helped me so much. She's my right hand, kind of, and she's a consultant right now. And with that, I finish my presentation, and I'd like to welcome you to AUB and Beirut whenever things are good for you to come. Thank you all for listening.
Thank you so much, Professor, for this very interesting presentation. I think now we can open the floor for questions. So if you have a question, you can either raise your hand, virtually raise your hand, or you can add your question within the chat. Anjali, you may ask your question.
Thank you for your presentation, Professor Chehab. It was really nice. My question is, so given the high impact that we saw from aircraft gear tie stresses deeper into the pavement, I was
Yes.
wondering what are your insights of, for instance, using inverted pavements as an option for airfields?
Increasing the boundary rate for airfields, you said, the last sentence?
Inverted pavements.
Inverted pavement? I'm not getting the last sentence. Your voice is kind of cutting.
Sorry. So yeah, what are your insights in using inverted pavements for airfield as an option?
Well, again, I mean, the top layer are still important. The surface layer is still important. And you might, I mean, we tried the Boeing 777, and that 777 is the heaviest aircraft that lands there. So we saw that, yeah, huge impact, but you might still have smaller gears, smaller aircraft where stresses are going to be extremely high on the surface layer as well. So so you cannot neglect the surface completely. I think both should be made of high quality. Don't underestimate the shear stresses at the top of the pavement, of the surface. So we can't neglect them. I mean, both are as important.
Understood. Thank you.
We have a question also from Daniel. You may ask your question.
Yeah, so thank you so much, Dr. Shaw, for your great presentation. It was really interesting. This is Daniel from University of New Hampshire. Currently, I'm working on a project which is somehow similar to your work, but I'm working on cracking side of things. I have two questions related to Flexpay. So the finite element model mesh in the Flexpay is based on the car load distribution within the pavement. And I don't know which version of Flexpay did you use, but we cannot change the mesh in the model, which has a great impact on your model and how it calculates the stress and the strain within the pavement, especially for boundary conditions, since you said you used 3 different configurations of different aircrafts. So what did you do about that, about the meshing?
I used a special axle, okay? And I tried just one axle, and it took me a bit more time. So I did apply the boundary conditions, but they were very far. So I mean, I kept increasing the distance from the edge of the gear to the edge of the pavement until the stresses didn't reach the boundary anymore. And so we didn't have that boundary effect. I don't know whether that's what you're asking or not. But more than that, in terms of the, going further into meshing and that, I really didn't do that. I just made sure that my mesh is not affected by the boundary conditions, and that's it.
So except for boundary condition, what did you do about the mesh itself? Because the mesh, the way how the Flexpay does is it's meshing based on the car load distribution within the highway pavements.
You mean under the wheels? You say under the wheel, right? Under one side of the axle. True. In
the whole model, in the whole pavement.
Yeah, but I mean,
you cannot change.
I didn't do anything different, to be honest. I didn't do anything different. I put the actual tire dimensions there. So everything was according, from the Boeing specs. I brought all the dimensions related to the gears and this between tires and axles and different gears, and I just I put it as is in the in Flexpay as a special axis, axles, special axis. So I didn't play with the mesh. I just use it as is.
Okay.
And I kind of before we ran it on this, we ran it on something that we were able to validate. So we ran it on a very simple case and made sure that it's giving us reasonable or close enough results.
Dr. Hernandez, you may ask your question.
Thank you, Isaac. Can you hear me?
Yes.
Okay, so thank you for your presentation. My question is, it seems like the model, it's all the variables that we know make the model run for longer. So we have the 3D finite element, you have the moving load, you have plasticity. So my question is, how long does it take to run one case and for how many repetitions?
Yes. I ran it for 20 years. Now there's a different version now. The version that I have took about 40 minutes per run. But what I understood is it is written, I think initially it was written in MATLAB, if I'm not mistaken. My last conversation with Dr. Kim, he told me that they are working on maybe, I don't know, I don't want to put his words in my mouth, but as I understand, it's going to be much quicker now by changing some of the code and the language. So what I used, I mean, this exercise I showed you is something that I've been doing for the last, I started like 2 years ago. So right now, if you probably approach NC State and Dr. Kim, they will be able to give you probably a newer Flexpay. I have Flexpay 1.0, I think it's 1.1 now or something newer that is much quicker, as I understood.
Professor Chehab, there is one question in the chat that is asking about what were the structural thicknesses for sections A and B?
The structural thicknesses?
Yeah, in the case study that are A and B. You mentioned that there is A and B. They're asking about this.
It was 14 centimeters, the surface layer, and 26 is the binder, 40 centimeters total.
Thank you.
Similar on both runways.
I see. Professor Tutumlur, you may ask your question.
Yes. Hi, Ghassan.
Hello, how are you?
Very good. Enjoyed your presentation very much.
Thank you.
And one question that I have for you, when I was watching, I realized you were emphasizing compressive stresses and strains in the asphalt layers a lot. So, but rutting is a shear strength phenomenon, right? Yeah. I was wondering if you had a chance to look at the shear stresses also. Or
no, 100%. I did look at the shear stresses. To be honest, but I didn't. I looked at them. I didn't concentrate too much on them, and I didn't look at how they are changing with respect to changes in asphalt stiffness at different gear types, because the model that I used is based on the compressive stress. So that's the shift model is based on compressive stress. I do understand what you're saying, though. I mean, shear flow is not model, but again, this model only covers primary and secondary region of the rutting and not the tertiary. So shear might be at a bit later stage than what I showed.
Sure, sure. Also, stress ratio is another one to look at. Yep.
Yeah. But it's very important to look at the shear stresses. I think I should do that next, to be honest. I want to see how shear stresses change as well.
Great. Thanks.
Thank you so much. I don't think we will, unfortunately, we won't have time for more questions. Thank you so much for this very nice presentation. It was very informative.
Thank you very much.
We were so glad to have you.
Yeah, thanks, Isaac, for this. Thanks you, Dr. Al-Qadi. And really, I know you guys at ICT are doing a superb job. Keep it up. I hope to see you
Thank you so
soon.
much, Professor. Thank you.
Bye-bye.